Okay, I'm going to do three projectile motion sample problems. They come from the page that looks like this, Understanding Projectile Motion. All right, so that's what we're starting with. Here's our first sample problem. Okay, so whenever you're starting a projectile motion problem, or really any problem, starting off with a good picture will make your life a whole lot easier. So give me a second here. So what we have a projectile is launched from the ground. It's launched from the ground. It is launched at an angle of 52 degrees with a muzzle velocity of 76 meters per second. Here's your 52 degrees. And it was 76 meters per second. Now this 76 meters per second, it is a vector. And that means if it's a vector, we're going to need to break it into components. But first, we're going to go ahead and keep seeing what happens. Okay. Now if you watch the other one, you saw that the projectile motion, there are 5 characteristics, and one of them is that we're talking about stuff that works parabolically, and that'll come into play in a few minutes. So this is what we're looking, this is our basic setup, and it wants to know the projectile's range. Now, projectile's range means it's delta x. Anytime you see delta x on this, range, that's what we're talking about. Projectile's range, delta x. So once you have an idea of what your picture is going to be, we're going to go ahead and create a data table, essentially, that has all of our variables. All right. And we're going to divide it up into x and y variables. We're going to start off with the acceleration on both of them. Acceleration in the x, acceleration in the y. Initial in the x, initial in the y. We're going to have final in the x, final velocity in the y. Running out of room. Our displacement or our range, our height, and our time. And the time is really important. That's what's going to be the most useful. Okay, we have our variables. Let's go ahead and give me 1 second. I'm going to make a copy of this. Okay. We're going to go ahead and we're going to put our information in. So, because projectile motion, the x component is constant, that means there's no changes to it. We know our acceleration is going to be 0 in the x. We know, all right, our initial in the x and our initial in the y. One thing you should always do when you have a vector velocity is to break it into components. So I'm going to go ahead and I'm going to take it and we're going to redraw it here. Here's our vector. It's 52 degrees. 76 meters per second. So we're going to take a few seconds and we're going to break it into its components. It will have an x component and it will have a y component. The x component of your initial velocity, that is adjacent to the angle. So it is h hypotenuse times the cosine of theta. So we're looking at 76 cosine of 52. And that is 46.8 meters per second. We're going to do the same thing on the y. Our initial velocity in the y, this angle right here, this component, this is opposite the angle, so we're talking about sine. So our initial in the y is the hypotenuse times the sine of theta, or 76 times the sine of 52. All right, that value is 59.9 meters per second. All right, we're going to use this. We're going to go ahead. We're going to put it into over here. So in our x direction, we know that our initial in the x direction is 46.8 meters per second. But we also know that because it's constant, that means that both of these share the same velocity. So it's 46.8 is simply the velocity in the x direction. We do not know the delta x, that's what we're looking for. We also are unaware of the time. In the y direction, it is in free fall, so it's negative 9.81 meters per second squared. The initial velocity based on our components. Okay, had to take a quick pause there. So we were talking about the initial velocity in the y direction, and that initial velocity in the y direction is what we got from the component. So we're talking about 59.9 meters per second. All right. There's nothing been said so far about the final velocity in the y. We'll leave a blank there in case we need it. Our delta y is, actually back it up. I apologize. Let's go back just a little bit because we do know something about the final velocity in the y direction. We know that this is parabolic motion, and that the nature of parabolic motion is that what happens on this side is matched by what happens on this side. So if we have an initial y velocity, and get this out of the way. If we have this initial y velocity over here, then because it's parabolic motion, we know that this exact same thing is happening over here. The only difference being that it is now negative. So your v final in the y direction is basically your negative v initial. So we do know something. We know that our final velocity is negative 59.9 meters per second. And pay really close attention. Any projectile motion problem, pay lots of attention to your signs. They'll be very, very important. Okay, so we know the acceleration in the y. We know the initial velocity. We know the final velocity. Nothing has been said about the height right now, so we're not going to worry about it. And time. We don't know that. Okay, so let's take a look. We need to find our delta x, but over here on this side we have 1, 2 unknowns. On the other side we have 2 unknowns, but we also have 3 things that we do know. And because we have 3 things that we do know, we can solve. So if the time is the same from here to here, let's go ahead and we can say that we don't need delta y. And we're going to use those 3 variables, acceleration in the y, initial velocity in the y, and final velocity in the y. We're going to use those 3 things to help us solve for t. Now the equation that matches this, and by the way, this is a very common equation for projectile motion for the y, is that delta y, our displacement in the y direction, is equal to my initial velocity in the y direction plus x. That's not going to work, is it? It's not going to work because we don't have delta y. So let's back ourselves up. We need one thing, whatever does not have delta y. We're going to use the simplest of equations to solve for this. It is our final velocity in the y direction is equal to our initial velocity in the y direction plus acceleration times time. And again, we're looking for time. First thing, we have to move over the initial velocity. Okay. This is where those negatives can become very important. So we've got final velocity in the y minus the initial velocity in the y is equal to acceleration times time, solving for time. Okay, from this point we can go ahead and put all of our numbers in. Okay, so time is equal to final minus initial divided by a. So we're looking at negative 59.9 minus our initial, which is a positive, so it's minus a positive 59.9 divided by negative 9.81. If you can see, having that negative is going to be really important. So we're looking at